So, like, I wanted to try to do something a little different. When I prepared the abstract almost 2 years ago, these results were recently published then, at that time, and now they're recently plus 2 years. And the presentation is divided into 3 groups of compounds, and I'm going to use the first one to introduce a subject that was not really in the abstract, namely whether we could get any extra information by measuring single crystals of magnetic susceptibilities of single crystals. Anyway, the first group of compounds is one compound we prepared and studied, and another one related to that, which was done by somebody else. And I won't talk about the magnetism except to mention that all of these have slow relaxation and magnetization. And I'll focus more on the structures and what we might gain or not gain if we had measured single crystal magnetic susceptibility. The first compound is a cobalt benzoate polymer, and the second group is a pair of dysprosium compounds with very similar empirical formula, but one is a polymer and one is a dinuclear dysprosium complex with a ligand that is particularly good at lodging lanthanoids. And the third group of compounds consists of 3 isostructural dinuclear hetero, that is transition metal and lanthanoid complexes with sort of an anisotropic ligand field around the lanthanoid, and all of these have slow relaxation, including the gadolinium complex. Okay, so cobalt benzoate is prepared under mild conditions, and in the paper, which is cited here, you can find all the details of the very capable collaborators who interpret the magnetism. And it has the one point that I want to keep in mind is that it seems to have exchange interactions of ferromagnetic nature. So cobalt benzoate has been around a while. It was first prepared, as far as I know, in 1925. And there are several hydrates. The one we characterized is a trihydrate in the sense that it's got 2 aqua ligands and 1 free water, in one unique free water in the crystal structure. The synthesis is just boiling the components in water, cobalt carbonate with solid benzoic acid. And then you let it sit for 3 weeks or so and you get crystals. Now, the preparation is a little bit iffy if you deviate from this procedure. For example, if you, instead of letting it sit for 3 weeks, evaporate the reaction solution to dryness, you get anhydrous version. Now, I'll say more about the structure in a moment, but basically, here's the first shot of the structure. It's a polymer, and the basic unit consists of 2 cobalt atoms bridged by 2 aqua ligands. There's a third bridge, which is the carboxylate fragment of the benzoate. Then, of course, to balance charge, there's another free benzoate in the structure, and there's a free water. Now, the triple bridge holds the cobalt atoms together at a fairly close distance. We'll come back to the structure in shortly. I wasn't going to talk about the magnetism, but will mention, and they're in the slides, which I presume will be available if this is being recorded. So you can find all the details in the paper, which was published a couple of years ago. Back to the structure. This is a structure that has a little bit of symmetry. The space group is I2 upon A, which which is a different orientation of a space group that could also be set as C2 upon C, which is a more familiar setting, I think, in most cases. Cobalt atoms on a center symmetry. There's a twofold axis that goes through, let's say, the first two atoms and the para carbon of the benzoate, right? And the cobalt coordination sphere is an octahedron, slightly compressed axially. This O1 is the benzoate oxygen, and its symmetry relative. It's compressed to the extent of this distance, and the axial cobalt oxygen distance is 92% of the average of the other two. And the octahedra are tilted with respect to each other. Maybe a bit of an optical illusion here, because the cobalt atoms are in a straight line. And depending on how you look at this, it looks like it may not be, because we get fooled by the tilting of the octahedra to the extent of more than 26 degrees. The red bonds here are the axial directions of the axial ligands, and they're canted at 26 degrees to each other. And there's one more item I'll point out. There is a best plane through this ribbon of the cobalt polymer. But the bridging ligands are not, and the two cobalts don't form exactly a plane. The triangle on one side, the pink triangle, makes a dihedral angle of 30 degrees with the gray triangle, the bluish triangle. Right, so this is not fully symmetrical, but it does have a best plane through it, and that will keep that in mind. And now we go to another compound, which is very similar and was published more recently by Honda and colleagues. And this is also bridged, the cobalt unit with two bridging aquas, bridged by sulfo benzoate. Now, this is sulfo. It looks a little strange because the three oxygen atoms are disordered 2 ways each. But this makes the polymer itself neutral, whereas ours was a positively charged polymer and required that extra benzoate to balance charge. Well, in this case, the crystals formed pretty well, it seems, to the extent that they made some single crystal magnetic susceptibility measurements. It's a different space group, but they have this similar arrangement of the cobalt polymer all in a plane, and the geometric parameters are very similar to the one that we characterized. The slight compression of the octahedra and short distance between cobalt atoms. And one other item, which they went to some lengths to point out, which is that the angle at the bridging oxygen atom, cobalt, oxygen, cobalt, is, they're in the range of 93 to 94 degrees. But what these authors pointed out was it was below 97 degrees. And 97 degrees is what they cite as the limiting angle for promoting ferromagnetic superexchange. Otherwise, the geometrical parameters of this are very similar to ours. And so the ribbon is in the crystal structure, same with ours. And here's the point I wanted to get to. All the ribbons in the structure are parallel to each other. When we look at a crystal structure, a crystal structure is solved for only the asymmetric unit, and that appears explicitly, and then the rest is generated by the symmetry elements of the space group. Sometimes we lose sight of the fact that the different symmetry-related molecules are not necessarily parallel to each other. In this case, they are, and well separated. So they measured magnetic susceptibility with the, in this slide is we have two references that they give for this limiting angle of 97 degrees. They measured magnetic susceptibility in single crystals with the magnetic field parallel to AB and to C star. And this being monoclinic, this is monoclinic also. C star is the axis that's parallel to A and B. So A, B, and C star form an orthogonal set. And C star happens to be the direction perpendicular to the plane of this chain, the plane of this ribbon, sorry, the chain would not have, a chain is one direction, but the plane of this plane through this ribbon is perpendicular to C star. So if the magnetic field there, and they see this response here in blue. Okay. So that raises the question, do we gain anything by measuring single crystal susceptibilities? And since we're here, I thought I'd explore this a bit and see what we might gain with our other two groups of compounds if we measure single crystal susceptibilities. Now, I'll mention in advance, this is a hypothetical study. We did not measure single crystal susceptibilities, but here's how you would do it if we did. It's all laid out in a book. It's in a couple of places, including publications. But Magnetism and Ligand Field Analysis by Gerlach gives details about how you would measure a single crystal magnetic susceptibility tensor, both with a magnetic field when you have a longitudinal magnetic field, that is, when your reference direction you've oriented the crystal along is perpendicular to the field, or when it's parallel to the field, in the longitudinal field, parallel to the reference axis, or perpendicular as it might be in a Faraday balance. Okay, if you have a triclinic crystal, that's a double-edged sword. You have, if you have a triclinic crystal with one molecule in the unit cell, that's the best case scenario for maximizing information because the crystal tensor is the molecular tensor. But for a triclinic crystal, you need to make more measurements. There's not a problem if you can find 6 axes to orient the crystals along and make the measurements. There's a set of equations. The C, eta, and zeta are direction cosines of the direction you've got the crystal down in the magnetic field, referred to some Cartesian axis pegged to the crystal. If you measure 6 directions, then the set of equations is linear in the components of the susceptibility tensor, and so it's just a simple matter to solve it. Now, how about getting 6 different directions? Well, I happen to know that Gerlach and his colleagues used to do that by eye, using Weissenberg photography to align the crystals just right. In Saragossa we have something a little different. This is a Huber optical goniometer that was modified by Huber. It's a 2-circle goniometer, so you can, in principle, orient in a large section of orientational space. And instead of the optics that you would normally have for measuring crystal morphologies, they put a receiving support where you can, well, here's how it works. Okay, the 2 angles are the 2 angles of an optical goniometer. There's a spindle axis, which is along the z-axis of the instrument in a local reference frame, and there's a rotation perpendicular to that. It gets you a lot of space. So the general procedure is you line up a crystal on an X-ray diffractometer. Here is a crystal on an X-ray diffractometer. This is not one that was used for magnetic measurements. But anyway, the diffractometer gives you an orientation matrix, and that relates the components of the reciprocal vectors, A star, B star, and C star, to a local reference frame on the diffractometer, which is Cartesian. So now I have a very good description and accurate of the crystal orientation. Transfer that still on the goniometer head to the optical goniometer. You can simply calculate the 2 rotation angles you need to set in order to align the crystal, or any direction in the crystal, real or reciprocal, with the receiving support, which is along the z-axis of the optical goniometer. All right? So there's no sample in this photo. This is just, so you take take your crystal from the diffractometer, put it right on, up here, right on the optical goniometer, set the angles so that the axis you want aligned this way is there, and mate the two supports. You gotta, it's not trivial to figure out what glue you ought to use for the first joint, because you got to remove it. And in general, and it's very often the case, you don't need to use glue. And you just transfer the crystal to the support, and from there take it to whatever measurements you want to make with the crystal aligned in that direction. So, with that in mind, however, it is worth considering whether you actually gain anything by measuring a single crystal in all cases. Now, if the crystal is triclinic, and as I say, you have one molecule in the unit cell, then you do gain with respect to the information you would have if you measure from a powder. But if we look at our other two groups of complexes, this may be instructive, because you don't always get the full molecular tensor depending on the symmetry of the crystal. For a second group of compounds, pair of dysprosium Pboa complexes. We'll see what Pboa is in a minute. One is a polymer with a staircase-like structure. One is a dinuclear complex with a fairly large distance between the two dysprosium atoms. This was all written up way back when, in 2017, and both of these compounds have slow magnetic relaxation, but I won't talk about that aspect of it. Well, Pboa is a great ligand. It accommodates metal atoms in a host of different ways. There are at least 9 ways known, and all of them except the one enclosed in the red ellipse here, all of the others have been observed for lanthanoids. And we're actually, in our two complexes with dysprosium, we observed 4 different coordination modes of Pboa. Well, the first compound, the polymer, both of these have similar empirical formulas too, by the way. It was prepared in very mild conditions. You just mix everything together, filter it, and crystals appear overnight, almost a gift. Now, the structure at first looks a little daunting, but it's not so much when we analyze its components. There's one unique dysprosium atom. The space group is orthorhombic PDCN. Dysprosium is surrounded by a monocapped square antiprism. And we can see here that the Pboa ligand attaches in 2 different ways. One has a trichelate and also bridges through a short bridge to another dysprosium, and one is a long extended bridge to dysprosium, another dysprosium atom. All the dysprosium atoms are related by symmetry. Well, the first one has one of these coordination modes that we saw in the previous slide, with three chelates and then the other dysprosium, right? Okay. And the long bridge has the arms extended mode, is bridging 2 dysprosium atoms. And the result of this is this staircase-like structure, right? And the question is, okay, what information would we get or lose if we measure a single crystal? Right? Now, there are a lot of different dysprosium distances here. I'll note the 13 angstrom one, because we'll see it again in the dinuclear compound. But if you take the best plane through this staircase, now there are a lot of, the best plane through a staircase is kind of a diagonal along its propagation direction. That plane is the 0, 2, 0 plane of the orthorhombic unit cell. And it turns out that symmetry then does not create new orientations. Other staircases will be parallel to this one. Right? So if the staircase is the basic unit we want to analyze, then we can do it with this orthorhombic crystal. And by the way, for an orthorhombic crystal, unlike triclinic, an orthorhombic crystal, the principal axes of susceptibility tensor are going to be along the A, B, and C axes of the conventional orthorhombic unit cell. So you only need 3 measurements.
Larry, 2 minutes.
Thank you. And for the second dysprosium compound, the ligand is in the arms open. One is in the arms open mode. That is disordered about a center of symmetry. So right there we already lose some information if we measure a single crystal. And the other ligand is the blocking ligand that through its coordination mode blocks the formation of a polymer. Right? Okay, now the question is, in this structure, are the different molecules in the unit cell parallel to each other? If they're not, then a single crystal susceptibility measurement will give you the average of all of the molecular tensors in their different orientations. We have in this table the distances between dysprosium atoms with the different numbers, but I've drawn some lines. For example, 1 and 2 are the 2 dysprosium atoms of one molecule. I've join them with a sort of lavender colored line, and 3 and this other one are the red. Right? And the angles between pairs of these molecules are not 0 in all cases. There's 16-degree angle between violet and red. Sorry, that's violet and red. And so right then and there, if you measure the susceptibility of a single crystal, you're getting an average of two tensors that are slightly tilted with respect to each other. Okay? We can analyze that for the third group of compounds, but basically it comes out the same. We have a structure in which this large ligand and then a second group of ligands, 3 chlorine atoms in a triangle, are not parallel to each other. This is an anisotropic coordination environment around gadolinium, which leads, we think, to the slow relaxation. And it's an anisotropic structure that if we were to measure a single crystal, let me go here. Let's use the plane of the 3 chloride ligands, as a reference for the 4 molecules in this case a monoclinic unit cell. The angles between these planes are either 0 for some pairs of molecules or 9 degrees for others. So even then, now it's only 9 degrees, but we're still losing information if we measure the single crystal with respect to what we would get if we could measure, hypothetically, a single molecule. We can argue that it's still better than what we get measuring a powder. And of course, for a single crystal, typically we need a bigger sample. We have some more characterization of the lack of parallelism between the molecules, but I'll save that for another day. And we do have more results regarding this last group of compounds, but I'll save that for the next one when we can all see it in person.
Yes.
That's it. Thank you very much, and thanks for your attention.
Thank you, Larry.
The ability to measure with a single crystal, that might not give the full information about the single molecule behavior, the magnetic behavior, but I guess we will agree that in systems that have long-range magnetic orders, so for the collective, when we are asking ourselves what is the collective magnetic behavior, this might be very, very important. So my question refers to the first group of compounds in which you went quite quickly through it, but you said that there are basically dominant ferromagnetic interactions, giving rise finally to an antiferromagnetic order system. So actually my question is whether you know about what is the nature of this magnetic order and why it is ordered in antiferromagnetic ways. Is it composed of ferromagnetic chains ordered antiferromagnetically, or do you have any clue?
Actually, I don't know. I can only refer you to the publication. But it does become antiferromagnetic at 5.5 Kelvin. That's on the slide here somewhere. Here you go. That's right. This was a sort of a global analysis And I don't think we went into if it's anti-ferromagnetic ordering or ferromagnetic interactions.
Did you measure the heat capacity of this sample near the phase transition?
No.
No, okay. Because this could tell you about whether the dimensionality is dominantly 1D or it has some crossover between 1D, which might be the ferromagnetic component, and the three-dimensional order driven by the chain interaction. But yeah, it is interesting. It's intriguing.
Yeah. And even more interesting that it's a compound that's been known for almost a century.
Okay.